One of the more common cases of constant acceleration is the acceleration due to gravity near Earth's surface. When an object is dropped, its initial velocity is zero. At a later time, while falling, it has non-zero velocity. So as it goes down, falling, it just increases its velocity further and further. So which means in every second, it is going to travel more distance. And as it hits the water, its velocity is actually not a zero, as many people are confused. So if we draw a velocity vector for each case, so we have no velocity at the top, and then we have a little velocity, and then we have, let's say if we're checking every second, so the velocity increases, and then it increases even further, and it's even further increases in the water. So watch out whenever the object hits the floor or ground or any place, any material, its velocity is not zero, although it might seem like it stops when the ball is dropped on a floor. It doesn't mean its velocity as it hits the ground is zero. Well, as the velocity changes, and we know what happens when a velocity is changing, there is an acceleration. So that means here, while it is dropping, there is a downwards acceleration that goes that accompanies the falling object. So this acceleration is solely due to the gravity of the Earth. We'll discuss the gravity of Earth later, but Earth causes the object to fall. If you, let's say, with some magic, you drop a ball, and then with some magic, the Earth disappears, then the ball will not fall because there is no Earth, no gravity. So this acceleration, because it's a special case for the Earth, we not, or for any planet, we denote it as a lowercase g. The magnitude of the gravitational acceleration, average magnitude of the value of gravitational acceleration. So sometimes we put the magnitude as these two lines next to each other, or we just drop the little arrow, equals 9.80 meters per second square. Remember, this is an average volume, which is also about 32.2 feet per second square. So this value is an approximation because in different locations on Earth, due to the differences in elevation and regional average mass densities of Earth, the gravitational acceleration could be different. And these small variations are ignored in this course at the moment when we solve kinematics problems. Another factor that affects the or reduces the acceleration is the air resistance of falling objects, but it is also to be ignored in our problem solving in this chapter. Just for simplicity, we will come back to air resistance later and its frictional effects. Objects in motion solely under the influence of gravity are said to be in free fall. The words free fall many bring to mind dropped objects. However, the term applies to any motion under the sole influence of gravity. Objects released from rest, thrown upward or downward, are all in free fall once they are released. In the first case, in my picture, you see just an object being dropped. So we could imagine an object that is being thrown downwards or upwards. So we have a dropping object, thrown object downwards, and thrown upward. So all these three cases are in fact free fall. So what's interesting is that in all cases, acceleration is always going, due to the gravity, is always downwards. So thrown downward object is still accelerating downwards, as you can see. And then it might be hard to understand why thrown object upwards is accelerating downwards. Just think of this. Remember, acceleration is change in velocity. As the object goes up, it will start slowing down. And at some point, it will just stop. So if we draw a velocity vector here, we have this object has a decreased velocity and then even smaller, and then velocity at a certain height will be 0. It's not the V naught, would be 0 meters per second. And then what's going to happen as it reaches the maximum height? So for certain initial velocities, it will reach to certain height. So maximum height. What will happen? It will just momentarily stop, and then it will start falling back again. So it will start falling back again downwards, and then it will be free fall like in a first case. Okay, so in any case, acceleration is downwards. The earth is pulling these objects down. The acceleration due to gravity has the same value for all freely falling objects, regardless of their mass or weight. It was once thought that heavier bodies accelerate faster than lighter bodies. You probably will be skeptical if I say, like, if you have a ping pong ball and you have a metallic ball with the sizes of a ping pong ball, both will land on the ground at the same time, because kind of your experience shows the opposite. But let's hold on that. So this concept of freely falling bodies, regardless of the mass or the weight, they will fall at the same time. They will experience the same gravitational acceleration. This concept was part of the Aristotle's theory of motion. So you can easily observe that a coin accelerates faster than a sheet of paper when dropped simultaneously from the same height. But in this case, air resistance plays a noticeable role. So if you crumble the paper into a compact ball, it gives the coin a much better race. So stop this video and actually try it down. So similarly, a feather floats down much more slowly than a coin falls. However, in a near vacuum where there is a negligible air resistance, the feather and the coin have the same acceleration, the acceleration due to gravity. Astronaut David Scott performed a similar experiment on the moon in 1971 by simultaneously dropping a feather and a hammer from the same height. He did not need a vacuum pump. The moon has no atmosphere and therefore no air resistance. The hammer and feather reached the lunar surface together, but both had a similar acceleration and fell at a slower rate than on Earth. The acceleration due to gravity near the moon's surface is only about 1/6 of the Earth's surface. So if I put the g of the moon, that approximately equals g on Earth over 6. So you would understand how lightly you would be walking on the moon, or how easily you could jump on the moon. And maybe you not maybe I am going to ask you to calculate how far could you jump on the moon. If you jump, let's say, half a meter on the earth with the same speed that you start with. Currently accepted ideas about the motion of falling bodies are due to, in a large part, of Galileo Galilei. He challenged Aristotle's theory of experimentally investigating the motion of such objects. Legend has it that Galileo studied the accelerations of falling bodies by dropping objects of different weights from the top of a leaning tower of Pisa. What did Galileo do? In contrast to Aristotle's approach, it was based on deduction. By the scientific method, for a theory to be valid, it must correctly predict or agree with the experimental results. If it doesn't, it is invalid or required modification. Well, Galileo said, I think that in the discussion of natural problems, we ought to begin at the authoritative place of scripture, but at sensible experiments and necessary demonstrations. This experiment of falling bodies by dropping objects from leaning tower done by Galileo, it's probably the most popular and well-known legends. There is some debate as to whether Galileo actually did this, but there is little doubt that he questioned Aristotle's view on the motion of falling object in 1638. He wrote, Aristotle says that an iron ball of 100 pounds falling from height of 100 cubits reaches the ground before a 1 pound ball has fallen in a single cubit. I say that they arrive at the same time. You find on making the experiment that the larger outstrips the smaller by 2 finger breadths. That is, when the larger has reached the ground, the other is short of it by 2 finger breadths. Now you would not hide behind these 2 fingers the 19 cubits of Aristotle. Well, I know it was long, and it's a quote from Growth of Biological Thought. So in case you're interested, you might want to read it. And there is also another interesting article, or you can read from Aristotle, Galileo, and Tower of Pisa by Cooper, coming from Cornell University Press in 1935. The most important point that Galileo recognized is that the freely falling objects fall with the same acceleration regardless of their mass or weight. Galileo gave no reason as to why all objects in free fall have the same acceleration, but Newton did, as we will learn in later chapters. Now, let's go back to the description of the motion. It happens to be that the set of equations for motion in one dimension with constant acceleration will describe the free fall as well. The only difference that we had in one-dimensional motion, remember, it's on a straight line motion. It was a horizontal that we discussed. Now it is a vertical. So it is customary to use y to represent the vertical direction. So for example, for this motion, I would just put y-axis. If you may remember, on a horizontal motion, we used x-axis. We will use for the displacement, we would use delta y, where delta y equals final position minus initial position. And as we agreed, I dropped the overdrawn small arrow because we're going to take into account the direction with a plus or minus sign. So it is also customary to consider that positive y is going upwards and negative y goes downwards. And if we say this free fall is a motion on a y direction, and since the acceleration is pointing towards negative y direction, acceleration due to the gravity, then I can say acceleration due to the gravity equals negative g. Remember, the value of g was 9.8, so it would be negative 9.80 meters per second squared. Sometimes we also denote this acceleration as in a y-axis, but let's do that later. Now, if we summarize the kinematics equations in here, then for vertical motion or free fall, which is the same thing, I mean, not the same, but when it is due to the gravity, it is the same. So it's a vertical motion. I can write, my first equation will be v equals v naught plus a y t, where a y equals negative g. In some books, you might see this equation written as v equals v naught minus gt. I do not prefer that. I prefer that we write plus ay, and then when you plug in the ay as a negative g, then you use the negative number 9.8. That would be our first equation. And the second equation, we get y equals 1/2 v naught plus v t. Our third equation will be y equals v naught t plus 1/2 a y t. Again, a y is negative g. And finally, our last equation, the fourth equation, kinematics, would be v squared equals v naught squared plus 2ay and y. So when I say y, we need, you may remember in my previous video, I defined y to be delta y, which is y final minus y initial, where the y initial equals 0. Okay, so in case your y initial is not 0, you could consider to have a little addition here to be delta y here, because we mean a displacement in reality. Okay, so thanks for watching. Stay tuned for more videos to come. I will solve more example problems in separate videos.